29, Maddie, would you please read the purpose? And relevance, Thomas.
This information is used to make eyeglasses and contact lenses.
And Davis, you'll be successful when?
When I can use the agreement of snow around the direction of the light ray or to find the type of snow the light ray is traveling.
Okay, so it says that we need 20 minutes, and boy, we got 18, 17, so we got to go at a pretty good clip here. Imagine a Segway scooter. That's these two-wheeled things. Anybody ever ride one of those? Are they fun? Yeah? Put down, please. Imagine a Segway scooter going from a paved road to a muddy shoulder. Draw its path. Okay, so as I draw it, I'm going to go from the middle of the scooter to that normal right there. At that moment, we're going to have one wheel in the thick, slow mud, and one is still going to be on the good traction road. That means that this wheel here is going to slow down, but this wheel here is going to stay fast. Can you imagine how that's going to cause this thing to turn? It's going to turn to the left, like that. The Segway makes a smaller angle. Remember, the angles are measured to the normal. So this is the angle of incidence, and this is the angle in the mud. I'm going to call it theta sub 2. Okay, now let's look at the opposite direction. You're going from the slow mud to the fast road. Again, I'm going to draw it from that normal to the middle of the Segway. This is the angle of incidence in this case, the initial angle. And at that moment, when it hits the road for the first moment, we're going to have one wheel on the good road, one wheel is still in the slow mud. One wheel is on the fast road. Can you imagine how that's going to make it turn? It's going to turn like that. And here's your second angle there. So going from one material to the other, where you have different speeds, you're going to cause things to turn. Same is true with all waves, whether it be sound waves, or earthquake waves, or water waves. When a wave gets a bigger speed, the angle to the normal gets bigger. Yeah, I want to get the word bigger, though, in both cases. When you get a smaller speed, the angle to the normal gets smaller. You can use the word reduced. If you have a reduced speed, you have a reduced angle. Something like that. So, there's a relationship between these angles and the speeds. And remember on your, in previous packets, we have this equation right here, n equals c over v. So the index of refraction for a material is related to its velocity. So if I have velocity is related to the angles, and the index is related to the velocity, it makes sense that we could have a relationship between this n and the angles. And here it is, it's Snell's law. N1 sine of theta 1 equals N2 sine of theta 2. That is known as Snell's law. N1 sine of theta 1 equals N2 sine of theta 2. N1 is an index of refraction for the first material, the material that the ray is initially in. Theta sub 1 is the angle made with the normal in the first material, and then we have the second material's index and angle. So, number 6, find theta 2. We're going from alcohol to ruby. Ruby is a glass kind of a thing, alcohol is a liquid kind of a thing, so we'd expect the ruby to be more dense. So it is going to be slower material. The more dense, the slower light travels through it. So it's going to slow down a smaller speed, so it's going to have a smaller angle. The theta 2 here is going to be smaller than 50 degrees. But how much smaller? That's what we're going to be looking at. N1 sine of theta 1 equals N2 sine of theta 2. N1, the index of refraction for alcohol, right over here, 1.36. Sine of theta 1 is going to be the sine of 50. Remember, two things. Number one, make sure your calculator is in the degree mode, not radians. The default on a lot of your calculators are radians. That's bad. And secondly, make sure it's the angle with the normal, not the surface. Okay, N2, Ruby, 1.77. Sine of the unknown. We're looking for theta 2. Pull out your calculators and we type in 1.36 times this, wrong button. 1.36 times 50 degrees sine equals, on the left-hand side I have 1.04. Just a brief moment, please. And then I'm going to divide both sides by 1.77. 0.588. But that is not my answer. This 0.588 is the sine of my answer. So I have to do the inverse sine, and I get 36. Okay, question.
So where did you use the 1.36?
Over here, we're given that alpha alcohol is 1.36 for an N.
Oh, it's going from alcohol into ruby?
Yep.
I don't understand what you meant about like the calculator part. In your calculator,
In your
same with me, right? Press mode, and then the third one down, it should be radian and the degree. Yeah, degree. It depends on the feature. Yeah, that's no.
There are many ways of measuring angles. 360 degrees for a whole circle, 100 gradients for a full circle, or 2 pi radians for a full circle. There's at least 3 different versions of measuring angles. Okay, next one. We want to find the index of refraction for this unknown material. It's going from glass into something unknown. Well, it is a bigger angle here. This theta sub 2, the second material that it's in, is a bigger angle than the initial, so we know that it has a bigger speed. It's going to be less dense than glass, but there's lots of things that are less dense. So here we go. N1 sine of theta 1 equals N2 sine of theta 2. N1 for glass. Okay, here we have glass, 1.65. There's actually lots of types of glass with their own index of refraction. But whenever you have in your homework glass, assume it's the one that's given to you in the table. Okay, sine of theta 1. The first angle that it's in is down here. It's initially in the glass at a 40-degree angle. N2, that's the unknown. Sine of 60. On the left-hand side, 1.65 times the sine of 40 is 1.06. Sine of 60 is 0.866. I'm now going to divide both sides by 0.866. And I get 1.22. That equals the index of refraction in the second material. So what is closest to 1.22 in our little chart here? Liquid carbon dioxide. So it looks like it's going from glass into liquid carbon dioxide. So maybe this is a beaker of the stuff, and we're shining light through it. Yeah, who knows what kind of razzmatazz secret agents do, or evil. Yeah.
It's the inverse of sine -1.
Yep. Okay, common mistake alert. Be sure to use the angle between the normal and the ray. Make sure your calculator's in the degree mode. How do prisms make rainbows? Each wavelength of light will refract to different degrees. This bending is called refraction. And every color will bend at a slightly different angle. So we can see here that light that is white light, combination of all the different colors, comes in, but the violet light will bend more than the red light, and so that breaks it up into the rainbow. This causes colors to spread out as it, goes through. As the lights, perhaps I should say goes into the glass, as the lights leave the prism, they refract again. There's one refraction when it enters the glass, changes speeds, and then there's another refraction, another bending, as it leaves the prism. So, at this moment, let's skip the think about your learning. Let's go to the board work. Find the second angle down here. Find that angle right now on your own. See if you can do it. Board work number 1. Just a moment, please. Compare your work with mine. And Nate, what's your question?
What kind of mirror? I already did the work. Sure. What kind of mirror magnifying?
Only a convex. All the time?
Only under certain circumstances. Okay. Questions on the first one? Yep. Second one. We are looking for the unknown materials index of refraction. Compare your work with mine.
For number 1, how do you like the inverse?
Depends on your calculator. Hang on just a second.
Is that what you went from?